started here. Okay, so this is homotopical fixed point theory. I went back to the beginning because I wanted to record it. I forgot to record it. This is a part of a program with my longtime collaborator, Bruce Williams, who passed away in early 2018. Here's a bio sketch of Bruce, which I don't want to go through again. It's kind of painful for me to think about losing him because he was a very good friend of mine. He was very influential on my career, and he was a great guy, extremely supportive of me. So let's get started. So the first part of this talk is largely a little bit of motivation. Fixed point theory, which I will define, really arose from differential equations. So differential equations is the study of flows. Solutions to differential equation are flows. And what is a flow? Well, in the most abstract sense, it's a continuous homomorphism from the monoid of non-negative real numbers under addition to the topological monoid of self-maps of a topological space X. Usually X is a manifold, okay, but it could be anything, right? So that's what a flow is. It is a monoid homomorphism. Now, usually you don't see that as a definition. Usually the definition looks something like the next slide. A flow is a continuous map X cross the non-negative reals to X, satisfying the condition that phi of X comma S plus T, well, there's the formula, you can look at it, for all X in X and all S and T non-negative real numbers. That's usually what you would write down. So that's a flow. It's a one parameter family of endomorphisms, which satisfies like a homomorphism condition. Okay, so now there is another kind of dynamics which also is studied, which is called discrete dynamics. What we just talked about is continuous dynamics, where we look at the monoid of natural numbers under addition. And then a discrete dynamical system is a continuous homomorphism from the natural numbers rather than the non-negative reals to the endomorphisms of a space. But additively, the natural numbers are generated by the number 1, and the value at 1 of the homomorphism is a self-map of X. Let's call it F. And so we can think of discrete dynamics is studying self-maps of X. And one of the important sort of concepts in discrete dynamics is to study stationary points. A stationary point is also called a fixed point. That's a self-map such that it's a point in X, in the space X, satisfying f of X is equal to X. F does not change X. Okay, so that's what a fixed point is. And the basic questions about fixed points are, does this given self-map have a fixed point? And if so, how many are there, right? How many fixed points are there? Okay, so I want to like connect up the two different types of dynamics. So let's consider a self-map of X and consider something called the mapping telescope. So the mapping telescope is a bunch of, you could take X and take the product with a unit interval where the endpoints of the interval are integers, and take a big union of those. In other words, we're going to take the disjoint union over all integers of X Cartesian product with the unit interval n minus 1 comma n. And we're going to divide out by an equivalence relation, where the equivalence relation is given by the slide X comma n is an integer, is identified with f of X comma n plus 1. So that's the identification. This is called the mapping telescope. And here's a picture of the mapping telescope. So each trapezoidal image there can be viewed as, actually I drew a picture wrong of the mapping telescope, but it's not quite accurate, but never mind. We're gluing each trapezoid to the next one via F. And I didn't draw it correctly. I should have drawn the right-hand side is smaller than the left-hand side. So this is not an accurate picture, but this gives you an idea of the mapping telescope anyway. It's a schematic. Okay, so what does this have to do with dynamics? Well, the self map, remember, is discrete dynamics. And the mapping telescope actually comes equipped with a continuous dynamics. There's a flow on it, a very natural flow given by this formula phi of x comma s. Remember, x comma s is a point in the mapping telescope and t is a time. So we evaluate the flow at that point by saying it's xs plus t. And this is sometimes called the suspension flow. So it relates discrete dynamics to continuous dynamics. Okay, we're never going to use this in the talk. This is just motivation. So in the end, a discrete dynamical system gives rise to a continuous one. A continuous one also gives rise to a discrete one by just considering discrete times, unit times. Okay, so the next thing I want to talk about is some algebra, some very elementary algebra. So suppose I have a finite dimensional vector space over the reals. I want to consider the following canonical homomorphism from the dual of V, tensored with V to the hom from V to V, the endomorphisms of V, which is given by the following expression, iota of a covector tensored with a vector evaluated at a vector V is given by the covector evaluated at V times X. So this is actually a very well-known homomorphism, and it's actually an isomorphism as long as V is finite dimensional. And you can check it's an isomorphism by just choosing a basis and verifying it by induction on dimension if you want. When V is dimension 1, it's obvious, for example. And then the homomorphism is sort of additive in the second variable V. So you could just sort of breaks up at a direct sum and you just check it. Okay, so the trace is gotten as follows. This is an invariant description of the trace. Usually when we say trace, we take the sum of the diagonal entries of a matrix, but here I'm not choosing a basis. I'm just using the homomorphism iota. I invert it, and then I compose it with the evaluation map, which takes a covector and a vector and evaluates it. So that composition gives a homomorphism from the endomorphisms of V to the real numbers, and that's the trace operation, the classical trace operation. Okay, so so that's the. How many of you have you both seen this description of the trace? You should know it if you haven't.
No, I haven't. Thank you.
This is actually the right way to do it, right? Okay,
I
now
haven't seen this.
but if you choose a basis, you'll see that an endomorphism is just a square matrix, and you're just taking the sum of the entries of the square matrix. That's really what this is, right? But it's better to have a definition that doesn't involve choosing a basis, right? And this is a definition that doesn't involve choosing a basis. It's coordinate free. Okay, the trace of the identity is the dimension of the vector space. That's one thing. And if you have a self map of a finite set, we can regard that self map as a permutation matrix. So that's an endomorphism of a vector space whose basis is S, if you like. And then the trace of that permutation matrix is the same thing as the number of fixed points of the self map F. That's obvious because the diagonal entries are +1. And every diagonal entry corresponds to a fixed point. So that's cool, right? And in particular, the trace is not 0 if and only if F has a fixed point. So this is actually like the very basis of almost every fixed point theorem you'll ever encounter, this kind of elementary stupid fact, right? That the trace of a permutation matrix, if you think of a permutation matrix as a self-map of a finite set, corresponds to if it's non-zero, you have a fixed point.
Mm-hmm.
This is like the dumbest thing in the world, but it somehow seems to be the basic fact that's underlying everything. Okay, so now I want to talk about the total singular complex of a topological space. So this harkens back to simplicial complexes a bit. So we can look at the vector space whose basis is the set of continuous maps from a standard n simplex into X. So that's a vector space. I've given you a basis, so you get a vector space. So then the basis elements are called singular simplices. And you can restrict a singular simplex to an n-1 dimensional face of delta n. There are n+1 such faces. So we can let dk be the restriction to the kth face, and then take the alternating sum of that restriction map, and that's a homomorphism. So that's D, and this gives you a way of passing between the vector space of singular n simplices to the vector space based on the singular n-1 simplices. And then D squared is 0, and this is called the singular chain complex of X, as opposed to the simplicial chain complex of X of an abstract simplicial complex. This is defined for any topological space. And this doesn't depend upon choices. This is actually a completely canonical construction. And the singular homology is defined by taking the kernel of the nth boundary operator divided by the image of the previous boundary operator. So that's the nth homology. That's a vector space. But we could have defined homology over the integers rather than over the reals. But we would, instead of using a basis, instead of using vector spaces, we would use free abelian groups with bases the singular simplicity. So you could have defined this as an abelian group, right, instead. And that's also useful to know. Okay, so the basic properties of homology is that H0 is a vector space whose dimension is the number of path components of X. That's very elementary to check just from the definition, by the way. You can just check that yourself. You just need to know what the last boundary operator is from S1 of X to S0 of X, what that's doing. If X is simply connected, that means the fundamental group is trivial, I mean, then the first homology is trivial. If G is a map of spaces, of topological spaces, then one has an associated homomorphism from the homology of X to the homology of Y. That's an important basic property. That's also obvious from the definition. And next one is not obvious. If X is a manifold of dimension D, then the homology vanishes above dimension D. So this is sort of an invariance of dimension property for homology. And if X is a compact manifold, then the compactness is sort of a finiteness property, then the homology is finite dimensional in all degrees, in every degree, homology is finite dimensional. And that's going to be important for us too. Okay, so these are the basic properties of homology. Oh, here's one more, which is going to be useful. If X is a convex subset of Rn, then the homology vanishes in positive degrees. That's also not so difficult to check. It requires a little bit of work. Well, more generally, if X is contractible, which both of you should know what that means here, because you're a topologist, it's going to have the same property. Okay, so these are the basic properties of homology I wanted to list. Okay, so now I want to talk about the Lefschetz fixed point theorem. So given a self-map F from X to X, its Lefschetz trace is the alternating sum in each degree. So of the trace of the map. That's the mailman. Let's hold on. Okay, that was the mailman. So anyway, we could take the trace in each degree and take the alternating sum. And since X, we're assuming here that X the homology groups are finite dimensional and vanish in all but finitely many degrees. In particular, if X is a manifold, this expression makes sense. It's finite. It's a sum of traces, and trace, these, so you're going to get an integer, in fact, when you do this. And in particular, it makes sense when X is a compact manifold. I just said that. And so you can form this trace construction. And this is called the Lefschetz trace. And the theorem of Lefschetz, which is dated from 1926, is if you have a self-map, then the Lefschetz number is non-zero. If that's true, then F must have a fixed point. That's the implication. So this gives you a criterion for deciding if X has a fixed point. Okay, so that's the theorem. By the way, the main tool, one of the main tools, but not the only tool in that theorem, is the thing I mentioned about permutation matrices. A self map of a finite set. That's one of the main tools, but not the only tool. For the theorem to hold, X should be a compact manifold or a finite simplicial complex. A corollary of the Lefschetz fixed point theorem is the Brouwer fixed point theorem, which you might know of, which is usually proved differently. So let F mapping the n disk to the n disk be a self map, then F has a fixed point. Proof, let F be the self map of the n disk, then we can look at the Lefschetz trace of that self map. But the disk is convex, so the homology vanishes in every degree except 0. So you can look at the trace of the homology in degree 0, and that's going to be the Lefschetz number. But that trace, it's elementary to check that the F0 is the identity. So, and H0 of the n disk, because the n disk is connected, is just the real numbers. So therefore, the Lefschetz trace is 1, and therefore there must be a fixed point. That's a corollary to the Lefschetz fixed point theorem, the Brouwer fixed point theorem. When n equals 1, the Brouwer fixed point theorem is a version of the intermediate value theorem you learn in Calculus 1. In fact, it's equivalent to it. Okay, so that's the Brouwer theorem. Okay, let's talk about homotopy. Two continuous maps from X to Y are homotopic if there is a map from X cross 0, 1 to Y, X Cartesian product 0, 1 to Y, such that F of X comma 0, oops, this is a typo, it should be lowercase x. The F of X, lowercase x comma 0 is F0 of X, and F of X1 is F1 of X, F sub 1 of X for all X and X. Or in other words, if we set F sub T of X to be F of X comma T, then F sub T is a map from X to Y and should be viewed as a path of functions, a path of continuous functions from X to Y, which starts at F0 and terminates at F1. So that's the idea of homotopy. Homotopy is an equivalence relation, by the way, on functions. So let's assume that F and G are homotopic self-maps of X. And we have this homotopy invariance statement that the Lefschetz number of F equals the Lefschetz number of G. So it doesn't depend upon the homotopy class of F. And the proof is that a basic property of homology is that the induced homomorphisms that F and G give on homology agree whenever F and G are homotopic. This is a basic property of homology. So that's so there's a homotopy invariance of the Lefschetz number. That's an important fact. There's also a corollary, which is a rigidity statement. Let's assume that L of F is non-zero. This is immediately obvious from the previous corollary that any map homotopic to F has a fixed point. So it's not just that F has a fixed point, but every map homotopic to it has a fixed point, because any map homotopic to F will also have a non-trivial Lefschetz number. So that's a rigidity statement. So therefore, the fixed points are not removable by homotopical deformation. That's what the corollary is saying. You can't remove fixed points. They're there. Any questions? Okay. So the Euler characteristic of X, which we're not going to use really in this talk, is defined to be the Lefschetz number of the identity, where the identity, the identity map of X. And this turns out because the trace of the identity is the dimension of the dimension, it's just the alternating sum of the dimensions of the homology groups. Okay, so there's a corollary to this, fact that I won't prove, that says that if X in Rm is a compact smooth N manifold with non-trivial Euler characteristic, then every vector field on X must have a zero, right? So I won't define what a vector field is, but the point is that somehow a manifold in Rm has at every point a tangent space, and a vector field is, roughly speaking, a choice of tangent vector at every point, which is varying in a smooth way. And so the point is if the Euler characteristic is non-zero, then every vector field must have a zero. And this has an application called the Hairy-Ball theorem. The Euler characteristic of the two-sphere, which we computed, I don't know when we computed it, maybe a week ago, 2 weeks ago, or maybe 3 weeks ago, we saw the Euler characteristic of the two-sphere using simplicial homology, which turns out to give you the same answer, is 2. So every vector field on the two-sphere must have a zero, and that's called the Hairy-Ball theorem. Because you can think of a vector field as like a hair at every point on the two-sphere. So this proves the Hairy-Ball theorem. Okay, so now what I'm largely interested in discussing in this talk is the converse to the Lefschetz theorem. What do we mean by the converse? So let's start off with a question which won't make much, which will be useless. Assume the Lefschetz number is zero, right, rather than being non-zero. What can be said about the fixed points of F? The answer is not much, since the Euler characteristic of the circle is trivial. But the identity map of the circle has fixed points. So not much can be said about F if the Lefschetz number is zero. This is not a good question, as stated. There is a better question. Suppose the Lefschetz number is zero. Are the fixed points of F removable? That's a better question, meaning, does there exist a homotopy of F to another map G such that G is fixed point free? Maybe we can get that to happen, right? Suppose the Lefschetz number of F is zero. Can I find a map G homotopic to F such that G is fixed point free? And that turns out to be true in certain cases. There's a theorem which is attributed to Wecken in 1942. Let X be a compact simply connected manifold of dimension at least 3. Let F be a self-map of X. If L of F is trivial, then F is homotopic to a map which is fixed point free. So it is known that first of all, this was not explicitly stated by Wecken. It can be deduced from what Wecken did. It first was stated, this result, by Fuller in his PhD thesis in 1951. Secondly, simple connectivity is necessary. There are counterexamples. By the way, I don't think this theorem is even true for surfaces in the non-simply connected case. I think it is true for the two-sphere, but the two-sphere is simply connected. So this is the Wecken theorem. It's a kind of converse to the Lefschetz theorem in the case where the manifold is simply connected. So this solves the problem more or less, except in dimension 2. In dimension 1, it's also solved. It sort of follows from what we know about one-dimensional manifolds. So you're really left with the non-simply connected case. So what can we say there? This is a typo. So the question is there a homotopy invariant? Meaning, is there an assignment of an algebraic quantity to a self-map, call it chi of F, such that chi of F is 0 if and only if F is homotopic to a fixed point free map? So is there some sort of complete invariant that works even in the non-simply connected case? We know the Lefschetz number is not good enough unless we're in the simply connected case. So is there a refinement of the Lefschetz number, if you will? So by a homotopy invariant, we mean an assignment of an algebraic quantity which does not change under homotopy. Okay, so I want to talk a little bit about Hochschild homology, but Hochschild homology for dummies. So dogs go away. So let's look at the fundamental group of our space. I'm assuming you know what that is. And let's define an action called twisted conjugation of pi on itself. So it's given by sort of conjugation. We define it in the following way. We say G times X is, this is really bad notation. I should have put an asterisk instead of a dot on the left-hand side. G times X is given by conjugation, not really, because we're going to first apply the value of F on G, F, the induced homomorphism of F on the fundamental group to G, and then inverting it on the right-hand side. So this is called twisted conjugation because it involves the homomorphism F. Okay. All right. So that's the action. And it is strictly speaking not completely rigorous. There's something you have to do to make it completely rigorous because F may not preserve the base point. So you have to do something about that, right? So I'm not going to worry about that here. Okay, so let lambda be the integral group ring of the fundamental group. So this is, as an abelian group, it's a free abelian group on the elements of pi, and it has a multiplication given by multiplication in pi, and then you extend it linearly. And it has a ring structure because you can add things because you're taking the free abelian group. The Hochschild homology in degree 0 is given by this H0 of lambda semicolon F. What you do is you take lambda and you divide out by the twisted conjugation relation. It's the group of co-invariants defined by twisted conjugation on lambda, right? So this is Hochschild homology. Okay. So let's remember that for the subsequent slides, that there's this Hochschild homology, which depends upon the action of the self-map on the fundamental group. So there's a theorem which is attributed to Veckin and R.F. Brown and other people, which goes something like this, but it's not ever stated by them in this way. I'm restating it. Let X be a compact manifold of dimension at least 3. Then there's a homotopy invariant which lies in the Hochschild homology, whose vanishing is both necessary and sufficient for finding a homotopy of F to a fixed point free map. So this solves the problem, except that we have to define the invariant, right? And I'm going to give you a sketch of how the invariant is actually defined in what follows. Okay, so now they never really state this result this way. This is a rewriting of history that I don't really know who first stated it this way. It's not clear, but I would give these guys the authorship because what they did was equivalent to this. There was a lot of rewriting. So I want to talk about something called homotopy fixed points. So first of all, let's recall what the fixed point set of a self-map is. That's the set of points in X such that f of X equals X. So that's a set, right? It's a subset of X. The homotopy fixed point is defined similarly, where you replace the condition that f of X equals X by the condition that there should be a path specified from X, the point X, to the point f of X. So it's a lambda is a path from 0, 1 to the space X, whose initial point of the path is the point X, whose terminal point of the path is f of X. So that's called the homotopy fixed point set. And obviously, there's an obvious map from the fixed point set to the homotopy fixed point set given by choosing the constant path at a fixed point. So there's a map from the fixed point set to the homotopy fixed point set. Okay, this is a key feature in what follows. Remember it. Now, a basic technical tool in all of this is transversality. We'll say that F is transverse, or rather sort of, it really means that F is transverse. The graph of F is transverse to the diagonal. I'm just going to say F is transverse if at each fixed point, x and x, we can consider the following linear transformation. We can take the identity homomorphism minus the directional derivative at the point x, and that's going to be a homomorphism of the tangent space to itself because we're at a fixed point. And we'd like that to be invertible. We'd like it to be non-singular. We'll say that f is transversal if at each fixed point this condition holds, that this is invertible. If this is the case, then the set of fixed points turns out to be isolated and in fact finite. So it's a finite set, the fixed point set in that case. Secondly, assuming f is transverse, then there's a number we can define. It's a sign. It lies in plus or minus 1. It's called the fixed point index of the fixed point, which is the sign of the determinant of the identity minus this differential, df sub x. And that sign of the determinant does not depend on a basis at all, because the sign of a determinant of a linear transformation from a finite dimensional vector space to itself does not depend upon the choice of basis at all.
No, it's
Right?
an
That
invariant.
what?
It's an invariant, right?
Right. So you don't have to choose a basis. This is completely well defined, this sign. And this is called the fixed point index of the fixed point. And this is a crucial number, this sign that should be, that's attached to the data. So if f is transversal, we can define this number at every fixed point. Okay? Every fixed point has a sign attached to it. Okay, and a key technical result about transversality is due to René Thom in the 50s. Given f mapping f to x, there's always an infinitesimal deformation, which means it's a homotopy, but you don't have to change f all that much. You can change f infinitesimally in some sense to a new self-map G, such that the latter map is transverse. So you can always move f to a transverse map. So you can just do that. You can always make it transverse. So finally, there's another tool that I want to introduce. I want to say a finite set F is signed. A finite set F is signed if it's equipped with a function to plus or minus 1. So it's called the signed set. It's a finite set with a function to plus or minus 1. So it's a label attached to every element of the finite set. And let alpha be a map from the finite set to a space Y. So now we have a signed finite set and a function from the finite set to a space Y. And then we can define a homology class in degree 0 associated to that data. It's what you do is you take the value of the function alpha at a point and multiply it by its sign, and then you sum up. And that's a zero-dimensional chain. It's a zero-dimensional, it's an element, it's a sum of singular zero simplices, if you think about it. It's a formal sum, and that gives rise to a zero-dimensional homology class. So a signed set with a function gives you a zero-dimensional homology class. This is a way of reinterpreting zero-dimensional homology classes, if you wish. Every zero-dimensional homology class can be interpreted in this way. That's kind of a neat way to think of it in a way. This is kind of my way. It's a new, I mean, it's not new, but it's like my way of presenting it. The way of presenting it is my way of presenting it. So this is how you can describe a zero-dimensional homology class. Okay, so what is this business with signed sets then? Well, we can define something called the Reidemeister trace. By the transversality theorem, we can assume our self-map is transverse without loss in generality. Then the fixed point set is a signed set because we have, at every fixed point, we have a fixed point index, right? Which is a sign. we also have a map from the fixed point set to the homotopy fixed point set. So we obtain the associated homology class, which we'll call chi of f in the zeroth homology of the homotopy fixed point set, right? That makes sense. And then this is called the Reidemeister trace of f, this construction. And by an elementary calculation, which I won't give, there's a canonical isomorphism between the Hochschild homology and the zeroth homology of the homotopy fixed point set. So this connects up algebra to geometry, if you will, right? The left side is algebra, the right side is geometry. So you can think of the Reidemeister trace as living in Hochschild homology because of this isomorphism. So we have the Reidemeister trace, okay? And this Reidemeister trace turns out to be the invariant you need for Weken and Brown's theorem. So that's the complete invariant in dimensions 3 and higher, which will, whose vanishing is necessary and sufficient to removing the fixed points of f. So now, what is the relationship of the Reidemeister trace to the Lefschetz trace? Well, there is a homomorphism from the zeroth homology of the homotopy fixed point set of f to the real numbers induced by the constant map from the homotopy fixed point set of f to the 1-point space. So that induces a homomorphism in homology, and then the image of that homomorph of the Reidemeister trace is the Lefschetz number, is the Lefschetz trace. So therefore, the Reidemeister trace is a refinement of the Lefschetz number. That's what this tells us. Okay, so now really the whole point of my talk is not to give a new theorem. Well, it's sort of a new theorem, but it's really more of a new method for solving these kinds of questions, which is called homotopical intersection theory, but let's call it for this talk Klein-Williams theory, right? That's what I'm going to call it, it was a theory introduced by Bruce Williams and myself in 2007, which is a very new way to sort of solve these kinds of problems. So the idea is that you can start with a fixed point problem and then associate it to something called a lifting problem, which is purely a question about algebraic topology. And then you can define an obstruction to solving the lifting problem, which is a total obstruction under certain restrictions, which is cohomological. And then that cohomological obstruction is related by something called Poincare duality to a homological invariant. And if the homological invariant vanishes, you've solved the original fixed point problem. So this is the approach of Klein and Williams in a nutshell. This is what we do. So I'm going to give you a small taste of it in this talk. It's really not going to do it justice, though. Okay, so here we go. So what is a lifting problem? A lifting problem is the following data. You want to fill in to make a commutative diagram, not on the nose, but up to homotopy. So you're given a map Q from a space P to space B. You're given a map P, lowercase p, from a space E to a space B. And you would like to find a map L, which is dotted, which fills in the diagram, not exactly, but only up to homotopy. So you want to find a map L from P to E, which is called the lift, such that P composed with L is homotopic to Q. You would like to solve this problem. Okay, it's like finding a solution to an equation in a sense, right? Finding such a lift. So this is a lifting problem. Lifting problems go back to the early history of algebraic topology, in fact. So now given a self-map of X, call it F, there is an associated lifting problem called the fixed point lifting problem. It's this. You can take the graph of F, which is the bottom horizontal arrow, which is the map which on the from X to X cross X, which sends a point say, y to y comma f of y. Okay, so that's the graph of f. And then the vertical map, which is an inclusion, which is what you do is you take x times x and you remove the diagonal from x times x. And what I'd like to do is solve this lifting problem. I'd like to find a map L which lifts the graph up to homotopy. Here's a lemma, which I think we were the first ones to really single this lemma out. It's absolutely trivial though. F is homotopic to a fixed point free map if and only if the above lifting problem admits a solution. So if we want to find a fixed point free map in the homotopy class of F, it's enough to solve the lifting problem. It's completely equivalent. So that's what we're going to concentrate on, solving the lifting problem. Okay. So the next, so that was the first step in my program that I sort of showed in the outline. The second step is to associate an obstruction, which we call the Euler class of a lifting problem. Assume X is a compact manifold of dimension. Actually, you don't even need a manifold in this step, but I'll state it that way. X is a compact manifold of dimension D not equal to 3. Turns out D not equal to 3 is important. Then there's a cohomology class in the cohomology of X with some twisted coefficient system, which I won't define, call it A, and the cohomology class vanishes if and only if the fixed point lifting problem has a solution. So I'm not going to give you an idea of how this solved, but if you've seen like the Euler classes before in vector bundle theory, it's a similar idea, right? Okay, so the Euler class is an obstruction to a nowhere zero section of the tangent bundle of a manifold. It's in the same spirit, this Euler class. So now our Euler class is much more general. And it turns out that our Euler class is not really the usual, in our generality, but in this case, we have a much more general one for our general theory, which doesn't lie in singular cohomology. It lies in stable cohomotopy theory, right? Which is another cohomology theory, which is much more powerful. Okay, so there's this Euler class. And then there's a third step in all of this called Poincare duality, which is there's a canonical isomorphism of abelian groups from the Hochschild homology in degree 0 of f of lambda with coefficients in f with the twisted cohomology in dimension d. And so we can define with respect to the duality isomorphism a class which corresponds to the Euler class, which we'll call chi of f again. And this chi of f doesn't require f to be transverse to define it. That's the beauty of all of this. We are not using transversality here. It's a different invariant, which will turn out to be the same as the Reidemeister trace under the assumption that f is transverse. And in fact, there's an index theorem. The obstruction that's defined by Klein-Williams theory coincides with the Reidemeister trace. That is the homology class defined by the map from the fixed point set to the homotopy fixed point set of F, together with the signed set structure on the fixed point set. So that is all for today. There's just one thing I'd like to bring up is the one reference that I want to give, which is this talk which is the paper that Bruce and I wrote about this, which appears in Geometry and Topology in 2007. So that's it for my talk. So I'm done. Any questions?
No, thank you.
Yeah. So that's all we got here today. No questions?
Well, just a general comment. You had asked, or you were considering topics for future talks. When I took differential topology with Professor Bruner many years ago, he mentioned that you were instrumental in solving some of the issues that Hatcher had raised or created in terms of surgery theory. So could you give a talk about that?
Yeah, that's related to this business here. In fact, that's actually contained in this paper.
Okay.
We fixed the literature in this paper. The literature was a mess. and it was wrong. And this is an answer to this paper by Hatcher and Quinn. So I can try to do justice to that, but it's going to take me at least 2 weeks to
No
write
problem.
something coherent. So I probably won't give a talk next week.
Okay.
Okay, I'll probably give a talk in 2 weeks
Sure.
if you're willing to be patient on that.
I'm patient.
Any,
And
yeah,
yeah, another topic, and if you want to talk about it, Michael Farber, you introduced me to the paper about topological complexity. If you want
uh,
to,
yeah, I can give a talk about that. That's pretty elementary, in fact.
yeah.
Yeah, maybe I'll do that. Maybe I can do that too. Okay, good to keep in mind. Thomas, you have any questions?
No, I got to take some time to think about it, actually.
Sure, but some of it was understandable, right?
Yeah.
Oh
Okay,
yeah.
okay, it wasn't like completely above your head, right?
No, I get the big picture, but I don't have I got to focus down my thought, basically.
Okay, great. So good to hear from you guys again. I'll see you probably in 2 weeks. Okay,
All right. Have a
Okay.
good
take
have
care.
a good week. Bye.
Bye.
Thank you. Thank you.
Thank you.